Welcome everyone to lecture 3 of Statistical Methods in Cosmology. You will have to bear with me today. I finally fell sick, so I'm not at 100% mode, but I'll do my best. So I wanted to finish talking about modeling of data and statistical inference, and some people asked me yesterday, what about combining different experiments or marginalizing over different parameters, okay? So I just wanted to talk a little bit about marginalization and combination of different experiments. Great. So perhaps, so why do we want to marginalize over different parameters? Perhaps, we are not interested in all of the parameters of our model at the time. And so if we are interested in a particular subset of the parameters, what we do is we marginalize over the other parameters, okay? And by this, I mean we integrate over the posterior distribution of all the rest of the parameters that are not the parameters of interest, okay? So when I say that I'm interested, say, in the probability distribution of parameters, I don't know, 1 to blah, 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 j, given the data, what I mean really is that I'm marginalizing over parameter j plus 1, blah, 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 until, all of the rest of the parameters. Okay, this is very common to do. In cosmology, you marginalize over nuisance parameters or perhaps over cosmological parameters. Perhaps you're just interested on a certain subset of the parameters. Now, another thing, so this is when we want to, marginalize over parameters, given a particular data set. Now, you may also ask, okay, you told us how to calculate the likelihood for a particular data set, but in cosmology, we have many different data sets, complementary to each other sometimes, or, and we may want to use information from different tracers in the universe. And so the situation becomes easy, in particular, if you have two independent experiments. In the case of two independent experiments, the likelihood is just the product likelihoods, okay? Because they are independent, they are probabilities. Of course, if the experiments, so let me write here. So, no, 1 second. Yeah, okay, this is very sensitive. Okay, so if the experiments are independent, likelihood is, let me write it in math, okay? Likelihood is the product of the likelihoods, okay? Likelihood is likelihood 1 times likelihood 2, okay? And we will study Fisher analysis, and we will see that this will translate in the sum of Fisher matrices. Of course, if the experiments are not independent, say I'm measuring the same observable with two different experiments that overlap in some portion of the sky, okay? We cannot multiply the likelihoods. So one has to include their covariance, right? Because they're going to covary. And okay, so that's in the more complicated case. So obviously, it's not always true that you can just multiply the likelihoods, okay? If the experiments, the experiments are not independent of each other, you need to take into account the covariance between the two. Sometimes also you may want to add a prior on a certain parameter, given, for example, coming from a different experiment, okay? Say, say I don't want to combine my CMB analysis with all the supernovae analysis. I just want to give a prior and say, okay, I will assume that I know omega lambda from supernovae, and I will do my CMB analysis, okay? In that case, you can just simply multiply by the prior, okay? You take the prior, the likelihood is given by the prior, okay? And you just multiply whatever likelihood, for example, say your, so means that if I have a likelihood, say, of the CMB, and I want to take some other prior into account, okay, I multiply by the prior of the particular, and to be consistent, I will call it alpha. I will not be consistent on what I call a parameter in all my lectures, but let's try, okay, on some particular, not all the parameters, but some particular parameter. Anyway. Okay. Greco had a question. This? Okay. So the question is answered? Okay, good. Okay, great. So, any questions about this? Yes. What's your name? Pedro. Mm-hmm. No, I mean, you still do the same. You know, more or less points. The question is, you still do the same, right? More or less points per se doesn't tell much. You may have a lot of points with very little information, or a few points with a lot of information. So, but in any case, the answer is you still do the same. Okay, so with that being said, I wanted to give a brief, or perhaps not so brief, overview of Markov chain Monte Carlo likelihood analysis, okay, which is a tool that is very used in cosmology and, you know, in other fields, like in particle physics as well. Susana, you had a question, or no? Okay. So, yes. So, this is what? 8. Okay. Markov chain, Monte Carlo likelihood analysis. I will write it MCMC in general, but I will write it here, Markov chain, Monte Carlo, MCMC, okay? Likelihood analysis. Great. So this is super useful. Basically, an MCMC is a method to simulate posterior distributions, okay? Basically, what you simulate is, you simulate sampling the posterior distribution of some parameter given the data using base, okay? So it's a method to simulate the posterior distribution of, say, some parameter given the data vector, okay? Using Bayes' theorem. So using Bayes' theorem, you will have that this is equal to, as I wrote yesterday, the data given the model, which is the likelihood times the prior over this normalization factor that in general just cancels out, okay? Okay, so why do we want a method to do this? So let me put some examples, okay? You may say, well, I could just explore the parameter space. The question is, you have some set of observations and you want to learn the posterior probability distribution of the cosmological parameters of some theory that you have, yeah? Say lambda CDM. You want to not only do the best fit, but you want to learn the posterior distribution. Okay, so let's say you want to constrain, I'll just put some examples to show you the power of the MCMC, or perhaps not the power of MCMC, but how bad we would do in the brute force case, okay? If we were just to follow a brute force scenario, yes? The parameters. Yeah, the model of the parameters of the model, yes. The data. Yeah. Okay, so say we want to constrain n cosmological parameters. N cosmological parameters. Okay, you may say, well, I'll just make a grid. Let's say, I don't know, let's take an example. For example, n is equal to 10. I have lambda CDM plus a few, 4 extra parameters, okay? I'm just taking some numbers that facilitate the calculation that I want to do. Okay, so let's say we want to allow each parameter to take 20 different values, okay? Okay, you may say, let's do a grid, right? Each parameter, not parameters, but parameter, I think this is what I want, yeah. No, okay, 1 second. Parameter takes m equal 20 values, okay? All right, so, okay, so then how many points do we have to evaluate? How many evaluations do we need to do? M to the n, right? So m to the n evaluations. In this very simple case, I mean, it's not a lot, 20 points, 10 parameters, it's something kind of, I'm having a standard model plus a few extra parameters, and I say, okay, let me evaluate it in 20 extra parameters. Okay, so what do I have? 20 to the 10, okay, evaluations. So let's say each evaluation, let's say each evaluation consists on evaluating the, solving for the Boltzmann equations to solve for the CLs of the CMB, okay? So for each, this means that for each evaluation, I need to run some of the standard codes, CAMB or class, okay? They take, several seconds, I would say, perhaps less than 10 seconds, but something like that, okay? A few seconds. It got better and better, so I don't know what's the latest status, but let's say order a few seconds, okay, each evaluation. If each evaluation takes a few seconds, this total number of evaluations would take 100,000 years, okay? Which means that if an early Neanderthal were to start the chains, this early Neanderthal would make it just on time to publish his results today. Okay, that's clearly not what we want. Okay, well, it would not be the same Neanderthal, but anyway. Why do we use MCMCs? MCMCs are a very powerful tool to overcome this problem, okay? They're basically a class of algorithms for sampling from probability distributions, okay? And so one can prove, I will not do it here, but one can prove that the state of the chain after a large number of steps is used as a sample of the desired distribution, okay? So the chain converges to the desired distribution. And that's the power of the Markov chain Monte Carlo likelihood analysis, because then I don't need to do integrals over probability distribution functions. You will see once you run the MCMC, you just have all the data. You can plot your posteriors. I will go over this. But if you converge to the desired distribution, then you're in business. So how does this work? Okay, so, and by the way, instead of the MCMC, instead of going exponentially, because this m to the n is going exponentially with the number of parameters, the MCMC goes linearly, okay? MCMC, powerful. It goes linearly with n, roughly linearly with n. And there are different algorithms. I will just explain one as an example, okay? So how does the algorithm work? Let's go to the relevant part, okay? We understood the problem. So how does the algorithm work? How does the algorithm work? Great. So I will consider here there are different algorithms that one could use under the umbrella of MCMCs. What I will consider is the Metropolis-Hastings algorithm, which is one of the simplest forms. There are other algorithms, okay? Nested sampling, Hamiltonian, Markov chain, etc., etc. But let me just, for the purpose of giving you an example, and it's the easiest example, let's consider the algorithm that we will consider here is the Metropolis-Hastings algorithm. And these algorithms, by the way, for you guys who are studying cosmology or working on cosmology, okay, these algorithms, these MCMCs, in my cosmology class in Boston, in Harvard, I make the students as a final project, one of the options is to code an MCMC by themselves. It's easy after I told you the recipe of how this works, okay? But, of course, when we do research, we don't code I don't code my own MCMC. I use standard packages, okay? There are codes. As you saw probably with Julian, probably talked about class, okay? There is class, there is CAM to solve the Boltzmann equations. There are standard codes that incorporate these Boltzmann solvers to do Markov chain Monte Carlo likelihood analysis. For example, they are called Cosmo MC or Monte Python. They have funny names. Anyway, so what does the algorithm do? The algorithm draws samples from the likelihood, okay? So it draws samples from the likelihood, okay? Okay, so the sample, I'm in a particular point in parameter space. What does that mean? That all the cosmological parameters have a certain value. I don't know, omega matter equals 0.5, omega lambda equals 0.7, blah, blah, blah. Okay, that's a point in parameter space. Okay, so the sample is, the sample, that point in which I am, is either accepted or rejected. Okay, how do I know if a point in parameter space is accepted or rejected? Well, it works as follows. We compare, so I draw a new sample, okay? My new sample will be X prime, okay? So then what do I do with X prime? I take the ratio, let's call this R, the ratio of the likelihood at X prime, which is a point in parameter space, over the likelihood of X, which is my previous point. I'm standing in X, I make a draw, okay? A random draw of another point in parameter space is X prime. I take the ratio, okay? Great. So let's call this T. Sorry, the present guy is T, okay? Where I'm standing now, present guy, present, okay? Now, if R is greater than 1, the likelihood of the new trial is greater, I move to that new point. I want to maximize the likelihood. I want to draw a posterior distribution following the posterior until I find the maximum, okay? And I want a lot of points around the maximum. That's our goal. So if R is less than 1, then the point T plus 1 will be exactly the sample that I just tried, okay? Now the question is, what happens if that ratio is less than 1? What do I do? Well, if that ratio is less than 1, I'm in a better likelihood point than the one I just drew, okay? So what do? I move or I don't move? Okay, so then you do the following. If R is less than 1, are you following? Yeah, okay. So if R is less than 1, I draw a random number, okay, from a uniform distribution. So draw a random number from a uniform distribution from 0 to 1, okay? Let's call this alpha, okay? Okay, so then if alpha is less than r, well then, you know, the likelihood was not that bad probably. And so then I move to the point in parameter space I just drew. You see? If alpha is greater than r, the probabilities that r were very low are, you know, it's more probable that r was a very low number. This is the thinking behind this, okay? So then I stay where I was, and I draw again. Yes, Mesut. Correct. And then you will find the extreme, in this case a maximum. Yes. What if the likelihood has two maxima at the same time? Because you found one extremum, you got stuck there. There is another peak that is lower likelihood, but it's still gradient zero. Then what do you do? Yeah. So, okay, so it could be the case when the likelihood, so that's a great question. And so an answer to that is that this algorithm works better when there is one maximum, okay? There are other algorithms, for example, nested sample or Hamiltonian Markov chain, that work better in those cases because they let you jump, they let you give bigger jumps. Okay, so this all depends on the jump that I'm doing, right? But there are other algorithms that, you know, take into account, that are better suited for many different peaks. Now, this may not fail for different peaks because imagine I have two peaks of the likelihood and I may be here, but I'm doing, you know, a big jump. So then I may be, you know, with big jumps, but it becomes more complicated if you have big jumps, and we will talk about the step size and how, you know, how that is an issue. But if the step size is too big, then you may be all the time doing this, and then it will be hard to map the full posterior distribution. So there is an art in choosing the best algorithm. But that's a great question, and in fact, many times I don't use this for lambda CDM works very well, but several times I don't use this algorithm and I use other algorithms because they are better at multi-peak likelihoods. Okay, so I said mathematically, so I told you the recipe, and I told you also that mathematically you can prove that this algorithm converges to the true likelihood distribution, okay? Okay, so yes, Neha, right? Yes, okay. You just make a random draw. Okay, so how do you choose X prime? Sorry, you make a random draw, but you follow given by either a proposal density or a particular step size. And we will talk about this, but yes. Randomly you're choosing this, basically. Or following certain prescriptions. Okay, so MCMC, and MCMC is really a fantastic tool that allows us to make parameter estimation using Bayes' theorem, okay? I'm always using Bayes' theorem. In the end, I will be using Bayes' theorem in a reasonable amount of time, okay? I don't have to wait 100,000 years, you know, these days you can wait several hours and you will have converged posterior distributions for a lambda CDM model. When I was a student, sometimes I waited for months for complicated models to converge. I think this is not the case. If I were doing the same models right now, it would take me a lot less. Anyway, So in practice, there are many things that one has to think about when doing MCMC analysis. For example, let me write here. Things to be considered. I will write, and I will talk about a few, okay? To be considered. Great. The step size is one, as I was telling to Neha. The step size that you choose for each parameter may be too big, maybe too small. You may say, okay, I want to move in omega lambda from 0 to 1, and I will move in step sizes of 0.5. Bad idea. That's too big, right? So there is an art in choosing the step size that you want. Or you may say, no, actually, I will not choose a step size. I don't want to be moving in parameter space like this, you know, in steps. What I want to do is to follow a proposal density. And a proposal density can be a covariance of all the parameters that you pre-calculated that takes into account correlations between different parameters, okay? So you may want to do so what I do, I'll tell you. Proposal density. What is this proposal density? Before telling you what I do. Say you have two parameters, okay? Parameter 1 and parameter 2. And they're very correlated, okay? This is their ellipse. So I don't want to move in parameter 2 in step sizes like this, because I know already that when I move, you know, and in parameter 2 in step sizes like this, because I know already that if I move a little bit on step, if I know beforehand how the dependence between alpha 1 and alpha 2 is, I may follow, it is a good idea to follow that dependence. How do I know beforehand? I could calculate it using Fisher and matrix analysis that we will see in a bit. Or another thing that I commonly do is the following. This is just like a recipe, really. There is no mathematical, I'm just telling you what works for me, okay? Which is, I start, if I don't know anything about the problem beforehand, okay? I start a chain with given step sizes on the parameters. I let it run for a while, not until it converges, and I will talk about convergence here, but for a while, okay, until more or less it's learning the correlations between the parameters. I calculate the correlations between the parameters at a certain point, not at the end, okay? And then I incorporate that as a proposal density so that I can move according to the eigenvalues and eigenvectors of this proposal density, yeah? Okay, so that's just a comment. There is the so-called burn-in period. What is the burn-in period? The burn-in period is that you may start different Markov chains, meaning this algorithm, you may start it at different points in parameter space. But you don't want the end result to depend on where you started, right? You don't want your posterior probability distribution to have the memory of the point where you started, because you're starting randomly at any point in parameter space, okay? So what people generally do is they discard, say, 10% or 20% of the first points, okay? So you count 20% of the total chain and you discard the first points so that you ensure that you don't preserve memory of where you started from, which is totally arbitrary, okay? That's the burn-in period. And what else do we have? We have efficiency of parameters, efficiency of parameter choice. By this, I mean the following. I'll not talk in detail about this, but we could talk at length. But by this, I mean, it is always easier to explore regions where parameters are not highly correlated, right? If I take omega lambda and then I take 2 omega lambda, that's not a very good idea. yeah, because the correlation will be a line, and it will be hard to map unless I know this from beforehand, okay? So choosing the parameters so that they are, not highly correlated, that in general is a good idea as well. Another thing that I want to talk about in more detail now is the convergence of the chains. When do I stop the chains? Convergence of the chains. Okay. So I want to talk now about a little bit about the convergence of the chains, okay? Any questions for now? Yes, Augusto. No, you can still use the proposal density to incorporate, the proposal density, even if it were a diagonal proposal density, at least you would know beforehand the size of the errors in the parameters. So you can always use proposal density, okay? Proposal density is more advantageous when it incorporates the correlations of the parameters. But in any case, even if it were diagonal, you would incorporate the knowledge of the errors on the parameters. Agustin. Augusto, hi, you too. Yes, okay, Augusto. No, I just invented a shape in which the two parameters are correlated. This is an ellipse, but this is an ellipse, right? Yeah. No, you may not always want that. I just invented a shape just to exemplify something, but it may be a circle, it may be whatever. Yeah, banana shape, you name it, just an example. What was your name? Gabriel. I will use the points that are not discarded, yes. I discard some point, I use the ones that are not discarded. All the steps that you made. Yes, all the steps, correct. Yeah. But when do I stop? That's the question, okay? Let's talk about convergence. The burning period is basically that you discard the first points, which are the points that you start from where you started, because you don't want to preserve the memory of a random place that you decided to start your chains in. Okay, convergence of the chains. Okay, when are the chains converged? So let me illustrate this by a criterion, basically a method proposed by Gelman and Rubin. Okay, this is known as the Gelman-Rubin criterion. Okay, so Gelman and Rubin no, this doesn't work here. Rubin in 1992 proposed the following method. So basically, they said that we should compare several sequences, okay, several samples drawn from different starting points and check to see if they are indistinguishable. So basically, let me illustrate what they propose. So let's suppose we have M chains, okay, and each chain, why am I writing so badly? Each chain has n elements, okay, has n elements, okay? So what they said is the following. Okay, so basically you can define the mean of a particular chain, here I will do the following, okay? So I will have a chain element. This will be a chain element, Y. J will denote the chain, and the element position will be given by I, okay? This goes from 1 to n, and this goes from 1 to m, okay? So we define the mean of the chain. The mean of the chain will be defined as, so I'm in chain J, and I will have 1 over n of the sum over I from 1 to n of y I j, okay? This is the mean of the chain J, all right? Now I will calculate the variance between chains and the variance within each chain, okay? And this guy said, before I start writing it down, this guy said that a good quantity, a good estimator of the convergence is the ratio between the variance between chains and the variance within a chain, okay? And we will take into account the numbers of this ratio, okay? The value of this ratio to have some standard of convergence, okay? So, okay, so formally what I mean is that you can define the variance between chains. The variance between chains will be, I will call it B, okay? And it will be 1 over m, 1 minus m minus 1 to make the estimator of the variance and bias. And today I will talk about, I thought I would, anyway, I'll tell you about unbiased estimators and minimum variance, which is something that I added because I thought it may be good for you to know how they are built following some questions that I had. So the variance between chains is given by 1 over m minus 1, the sum of j from 1 to m, y mean j minus y mean squared, okay? And the variance within chains, the variance within chains, I will write it as W here, and this is 1 over m, n minus 1, the sum over I and j of y I j minus y j squared, okay? Yes? The mean value of y, sorry, the mean value, yes, where is it? Anyway, I had it previously. The mean value, yeah, the mean value of j, and then, yeah, I sum over all the chains and I divide by m. Yes. Okay, great. So the quantity, the ratio, I can calculate R, okay? You will know this as the R statistics or the R minus 1 statistics sometimes in the literature, or the Gelman-Rubin criterion, okay? This is very, very popular to use. So here, what you will have is the ratio between the variance between chains over the variance within a chain, okay? Okay, so basically, if this, let's say this ratio is 1.03, just to give you an example, okay? Then I would say, okay, we are 3% converge. Why am I saying this? Because the variance between chains is a little bit higher, but almost the same as the variance within a chain, yeah? You don't want the variance between different chains to be humongous compared to the variance within a chain, because that would mean that I'm having very different values from chain to chain. That's not converged. The same model of the universe should give you the same value, right? The same posterior probability distribution in chain 1, chain 2, and chain 3, okay? So you see, if this value is very large, it's a problem, because why am I having a subset of values that is completely different to another subset of values, yeah? So you want this number to be close to 1. And so, okay, so basically what I want to say is you want R to be close to 1, okay? You want R to be close to 1, and there are different thresholds that it's basically subjective. You know, it depends on you. I don't know. What do you consider convergence or not? I tend to consider convergence 1.01, so I can say that my chains are 1% converged, but that's really up to you, the threshold that you put. Yes? Yes, I subtract, exactly, yes. So I started with, say, a chain with, I don't know, 2n, and I disregarded, yeah, good point. I disregarded n, so I end up with n points, okay? Okay, so that's a way. Well, when R is large, the variance between chains is way larger than the variance within a chain, okay? So it means that the values, the chains differ between each other a lot more than the points within the chain, which is bad, right? Because they should give you the same probability distribution. Well, so that it cannot happen really. So the variance within a chain, so that would mean that the variance within a chain is much larger than that cannot happen. Yes. That's a good question. I don't have. That's a good question. Some people have rules of thumbs. They not always work for me. So I don't want to give you my rule of thumb. I tend to run, you know, for lambda CDM, I run 4 chains. In general, it's good to run many chains, but if you run many chains, then you have to wait a lot more than you need for convergence, you see? The more chains you run, probably the better, right? But at some point you have this balance between how much you wait for convergence and how long do you wait for convergence. 1 chain, bad idea. That's for sure. You don't even have a convergence criterion. Or you may have, but not this one. Anyway, what did I want to say about burn-in? I think I said it. Basically, you disregard the first points. Yes, I wanted to say something else. Yes. So what do you do when you have the values of the MC? So you may have in Cosmo MC, for example, when you run Cosmo MC, you have, you know, lines, rows of different values of the parameters, okay? So this is parameter 1, parameter 2, parameter 3, blah, 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 all the values of the parameters. It also tells you the likelihood, okay, in one of the columns, and it also gives you the weight, okay? Weight 1 of the first sample that you ran. This is weight 2, let's call it likelihood 2, and parameter, whatever, other parameters, okay? Alpha 1, alpha 2, blah, 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 yeah? So what are these weights? Okay, you have all the parameters, the samples that you consider, you stepped in different positions in parameter space, you have the likelihood. Now you may ask, how do I compute the posterior probability distribution? So these weights are proportional, basically are the number of steps the chain weighted at a certain position, okay? Imagine I'm at close to the maximum likelihood. probably I will wait here for a long time, because when I draw another sample, probably the likelihood will be lower, okay? So the points close to the maximum likelihood will have higher weights, right? The weights are given by the number of trials that you try before moving to the next step, okay? So the MCMC, what you can do then is to use those weights, basically, to perform a kind of integration, but without performing the integration. So the density of points in some point in parameter space will be proportional to the posterior probability distribution, okay? So the higher the weight, the higher the posterior probability distribution will be. And that's the magic, that's the beauty, not the magic. We are doing science here, not the magic, but the beauty of an MCMC, right? That the density of points is proportional to the posterior. So you don't have to integrate over parameters. You already have it there. And so then you can just, you can order the different points in parameter space given by their weight and plot the posterior probability distribution. Yeah? And so basically, so then you can do other things. So once you have the posterior probability distribution, imagine you say, no, I forgot to include this data set. Well, if you think that the data set that you forgot to include wouldn't change the posteriors too much, then you can do what is known as post-processing, okay? Which is to add the likelihood, add the prior that you have, that is given by the second data set, as a multiplication on the likelihood, okay? So you basically are, you can add it a posteriori, okay? Basically, you multiply the prior that you have to the posterior probability distribution that you get from an MCMC. That's called post-processing. And that only works, not always works. It only works if you think the posterior that you get, you're adding a little bit of information, not a lot of information. Because if you add a lot of information, your parameters may be peaking at another point, okay? So you may have to rerun the MCMC. Anyway, post-processing is another story. Any questions about this before I move on to Fisher analysis? Questions? Shao? Yes. Oh, could you raise your voice, please? Sorry, I didn't understand. How can I what, sorry? Marginalize, you said? So, okay, so we will study, I will tell you how to margin. Once you have the posterior, you have all the posteriors, okay, from all the parameters. Once you have the posterior, you can play around with the posteriors, and I will show you in Fisher analysis how you can play around with the posteriors, okay? Okay. Yes, okay, so let me start by saying that, okay, I will start with Fisher forecast analysis now. This is what, 9? Okay, 9 is Fisher analysis, okay? This is very useful when you want to design a survey or you want to have an idea. It's based on a lot of approximations, okay? So it's not exact. It's a bad idea to analyze your data using Fisher analysis, as you will see, but it's a good idea when you want to have a back-of-the-envelope calculation of how can a future experiment do. And by that, I mean how well it can measure certain parameters, okay? Okay, so how does this formalism work? Okay, I wanted to tell you something else. Okay, so basically, this is the way you can define a Fisher matrix. You can expand the log likelihood in a Taylor series, okay? So you will have the log likelihood, and you will expand it in a Taylor series around some fiducial model that you choose. You have to choose a fiducial model. In general, it's a good idea to choose the fiducial model close to the best fit, okay, for reasons that you will see now. Okay, so if I expand this guy, the log likelihood, around the fiducial model, let's call the fiducial model theta 0, okay, fiducial model, then what do I have? Okay, I have this, which is a constant, plus 1/2 of the sum over ij of theta I minus theta I0 times the second derivative of the log likelihood with respect to theta I, theta j, evaluated at theta 0, okay, times theta j minus theta j 0. What happened with the first derivative? It went to 0 because I'm evaluating at the fiducial model. That's the maximum likelihood, okay? So in case you're wondering, here, d log L, d theta I at theta 0 is 0, okay? Great. So I can define the Hessian, right? The second derivative, the Hessian will be minus second derivative of log likelihood with respect to I with respect to j. And the Fisher matrix will be exactly the Hessian, okay? So the Fisher matrix, the Fisher matrix will be defined as follows. Okay, let me actually define, well, let me write it. So the Fisher matrix, where I and j are different parameters, will be minus the second derivative of log likelihood with respect to theta I, theta j. Okay? This is the Hessian. Okay? So the Fisher matrix encloses information on the parameters errors, okay, and their covariance. And so if the covariance is not diagonal, I'm taking into account correlations between the different parameters, yeah? So if two parameters are correlated, they may have a similar effect on the data. They may not necessarily be coming from the same physical process, but they may happen to have a similar effect on the data, okay? Okay, so the Fisher matrix, basically, it plays a big role in forecasting errors from a given experimental setup, and you can see, it's given by the curvature of the likelihood, okay, at a particular fiducial model, yeah? So you can see that if this curvature is very peaked, the errors on the parameters are well defined, okay, they're small, and if this curvature is broad, the errors on the parameters are not going to be very good, okay, the errors will be larger, yeah? The peak of the likelihood, the more peaky the likelihood is, the better the errors, okay? So if this is the likelihood, this likelihood has better errors than this likelihood, okay? Better errors on parameters than this guy over here. Okay? And so, great. So, also, we have seen that likelihoods of two independent experiments go as a product, right? So, two independent experiments will have a sum. So, to consider the Fisher matrix of two independent experiments, you just have to consider the sum of the Fisher matrices, okay? So, if you have experiment 1, and this one has Fij 1, and you have experiment 2, and this has Fij 2, then the total Fisher, the element ij total, will be 1 plus 2. Okay, ij. Okay? Great. So, okay. So, in the one, let me see. Actually, well, let me say a few other things here. Let me say the following. In the one parameter case, if you have just one parameter, if you think back at the Taylor expansion, you can show the following. So, for one parameter, you can write delta log likelihood is equal to 1/2 f, okay, 1, 1, okay, times theta minus theta 0 squared, okay, 1, 0 squared, okay? So, if 2 delta log likelihood is equal to 1, okay, if 2 delta log likelihood is equal to 1 and you identify that thing 2 delta log likelihood with chi squared, okay, corresponding to 68% confidence level, then you can see, so if this guy corresponds to delta chi squared and this corresponds to just 68% confidence level region, okay, delta chi squared of 1 for 1 degree of freedom, yeah, then you can see that 1 over the square root of f11 is the 1 sigma displacement from theta 0, okay? This is the 1 sigma displacement from theta 0, okay? Okay, so yeah, so basically you can have a case in which you marginalize over parameters or not marginalize over parameters, okay? When you don't, in general, nobody doesn't marginalize over the parameters, but I will write for completeness, I will write that basically the Fisher analysis will rely on the Cranmer-Rao inequality. This says that the standard deviation for parameter I will be greater or equal, than the following. It will be greater or equal than the 1 over the square root of the element II, okay? This is in the unmarginalized case. You probably never want to think about this case, but I'm writing it out for completeness. I never use it. Unmarginalized case. And when you want to talk to the different, to the rest of the parameters, what you do is you invert the matrix F. So when you invert it, all the parameters are talking to each other, okay? You take the square root and the element II, okay? So that's the error, that's the bound on the Kranman-Reyer inequality. So you take the square root of f to the minus 1, and then you take the element II. This is in the marginalized case. It's easy to remember because in the marginalized case, you want to talk to the rest of the parameters, and a way of talking, you can only talk to the parameters when you actually do something to that. You invert the matrix, okay? Okay, so I want to point out a few things. First of all, you can see from here that this gives us a bound on the errors. In general, people report the lower bound on the errors, yeah? But you see, this is the best possible case scenario, okay? And we are considering the likelihood to be, you know, we Taylor expanded around the maximum. The likelihood is Gaussianly distributed here, okay? So I'll show you for a Gaussianly distributed likelihood how we can write the Fisher matrix. Yes. So when people report the errors coming from Fisher forecast, those are the best possible errors that you can get in the most idealized scenario. But well, it's something, okay? Once you depart from that idealized scenario, which is always, you will get worse error bars. But it gives you some idea, okay, of something as opposed to not having any idea. This is better, okay? Great. What else do I want to say? You can show that you can write down the Fisher matrix as follows. Taking the likelihood as a Gaussian likelihood, as I wrote it in the previous class, okay, you can write down the Fisher matrix as 1/2 of the trace of the covariance to the -1, C comma I, which is the derivative with respect to parameter I of the covariance, C to the -1, C comma J, okay? This means the derivative with respect to parameter J, okay? Plus the data vector or the fiducial model. You don't have data in general for this, okay? You may work with data, but in general, for these cases, you're working with a fiducial model that you think you're making it behave as your data, okay? Your fiducial model is as if it were your data. So then you have your data vector, comma I transpose C to the -1, your data vector, comma J, okay? You can show that you can write the Fisher matrix in this way. And if you need, I leave you as a homework to show this. You will be using, okay, you will be using the fact, if you want to show this, you will need to use the fact that the log of the determinant of C is equal to the trace of the log of C, okay? Remember that we had a determinant of C when we wrote the likelihood, and now we have a trace. That's how it appears, okay? Okay, what else did I want to say? Okay, let's do something. Since I'm running out of time, I will show you, next class, I will show you how to compute ellipses. The plan is going to be as follows. I will show you how to compute ellipses, okay, marginalizing over parameters for a Fisher analysis. Then I will move on to show you how, and which is a little topic that I added, which came out from questions that you guys asked, how to generally compute a minimum variance and bias estimator, okay? And then I will start talking about a method to learn about non-Gaussianity from the data, which is closely related to, well, it is what I have been working on with my group. So I thought in the last lecture I would tell you a little bit about what I have been doing with my group. Okay, so that will be the plan. Questions? Yes? The likelihood has a yes. Here you're considering that the likelihood is Gaussian. This Fisher analysis, matrix analysis, is very idealistic, right? It's like the likelihood is Gaussianly distributed on the data, on the parameters, and I report an error that is the best possible error that I can have. Anyway, all sorts of assumptions. But Gabrielle. Yeah. No. Here, no. Chains, you can have one experiment and many different chains. Here I'm talking about, you should think about it as an analysis of two different experiments. Here it was in the context of Fisher analysis. But in the context, yeah, here I was talking about the Fisher analysis, okay? But is this clear to everyone? MCMC chains are not coming from different experiments, okay? You may combine different experiments and run the same chain, but if you have 4 chains, doesn't mean that you have 4 experiments anyway. More questions? Yes, Greco. The purpose of the Fisher matrix analysis is to have an estimate on the error of the parameters when you don't have the data at hand, and so you cannot run an MCMC with the data at hand, and you want to do a fast estimate. It's very useful for survey designs, right? So, you know, I have been working on the design of this proposed experiment, CMB stage 4. And the first part of the design of this experiment was basically running Fisher analysis, a little, you know, with different levels of sophistication, but it is this. It's running Fisher analysis and seeing, okay, if I change the survey design, you know, because in the covariance, you have the noise, a model of the noise of the experiment. You have the portion of the sky that you see with the experiment. The more sky you see, the less, the smaller the covariance, okay? You can add a model of the noise to the signal here in the covariance as well. Yeah, you will have covariance coming from cosmic variance, but you will also, for the CMB, for example, I'm talking about the CMBS4, but you will also have noise coming from the detector, and that you can model it so that you have it, you can do an analytical estimation of the errors. But in general, is to have an estimation of the errors. I would say A, because you want to do a survey design for a future experiment. You're trying to design it. That's what we did in the first step. Now they are building it, okay? But it's based on these designs. And the second thing is, you know, sometimes you want to work on a project and you want to have, you don't want to waste a long time, months and months in something that may not give you, you know, a good measurement on parameters. Say you're interested in measuring the matter content of the universe and you have some idea of using some observable. Instead of wasting or perhaps spending months and months on running, you know, running an MCMC and doing the analysis, sophisticated data analysis, to end up having very bad error bars, what you can do is do a quick Fisher analysis estimation. This tends to be quick, it's all analytical, okay? So you can do a quick Fisher analysis estimation and see if the project is worth pursuing or not. I recommend doing that. Yes? Yes? Good, yes, so this depends on the fiducial model, right? So you may say, how do my errors, the errors that I will get are around the fiducial model. But perhaps, you know, you may be, so the question is, if you are, you know, if this is the posterior of a certain parameter, okay, alpha. This is P of alpha. And this is your fiducial model, alpha F1. Alpha F1, okay? Okay, well, the 1 sigma error will be something like this. Of course, if this is my fiducial model, well, first of all, that's a bad choice of fiducial model, but the errors, the 1 sigma error from this point will be different, right? So you may want to, the error estimation will depend on your fiducial model. And perhaps you don't know the posterior beforehand, so it's not obvious where to take the fiducial model. So sometimes people report, especially for parameters that have not been well measured yet. So sometimes people report the errors around this fiducial model or the errors around this other fiducial model, okay? That's common to do. Yeah, it's a useful thing to do. Yeah. 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 Absolutely. Wait, an MCMC you said, or? Yes, and in general, but you use Bayes theorem for the MCMC. But I agree with you that, so the priors, you can incorporate them in the MCMC if they're informative or they're non-informative, you can always incorporate them. If there is anything else Bayesian apart from that's how I use the Bayesian, the Bayes theorem, yes, to calculate the posterior. Is that? I think I understand what you're saying because you're sampling from the likelihood. Is like you're saying. Yeah. If I understand correctly, right, is like sampling from the likelihood, not from the posterior, if the prior is non-informative. I agree. Okay. If there are no more questions, we'll stop now. I think in the program the talk is, I'm giving a talk today for the ones who speak Spanish at 6, but in the program is at 7. So if you were going to come at 6, not at 7. Okay. You're all invited to come.